The proliferation of autonomous AI agents in 2026 presents unprecedented operational complexities. System failures, often stemming from opaque decision trees and unmanaged interactions, demand a rigorous engineering discipline. How do we design agent systems that reliably pursue goals without constant human intervention, yet remain auditable and safe? Loop engineering, in its 2026 manifestation, describes constructing autonomous AI agent systems. Unlike classical feedback control, it designs agents to build contextual awareness, dynamically invoke diverse tools, rigorously verify outcomes, manage memory, coordinate subagents, and iteratively pursue complex goals. This process continues until predefined stopping conditions are met. It ensures goal-directed, resilient autonomy across intricate operational landscapes, moving beyond simple task execution to encompass true cognitive loops. Designing these agents necessitates a formal framework, the Loop Specification. Without it, agent behaviors become unpredictable, debugging grows intractable, and system reliability diminishes significantly. A comprehensive loop specification provides the blueprint for an agent's operational cycle, articulating its boundaries, capabilities, and decision-making heuristics precisely. It transforms an ambiguous AI aspiration into an engineered, verifiable, and manageable system, crucial for robust deployment in critical applications. Every autonomous loop begins with a trigger, the event or condition that initiates an agent's execution cycle. Triggers can range from external API calls, scheduled intervals, internal state changes, to sensor input exceeding thresholds. Defining the trigger precisely is paramount, dictating the agent's responsiveness and overall efficiency. An ill-defined trigger might lead to unnecessary activations, resource waste, or critical delays in responding to vital stimuli. The goal is the desired terminal state or outcome an agent strives to achieve. It must be explicit, measurable, bounded, and technically achievable. Vague goals inevitably result in erratic agent behavior and an inability to objectively determine successful completion. A well-articulated goal, such as reduce cloud spend by 15% without impacting latency, provides a clear directive, allowing objective verification of the agent's efficacy throughout its operational lifespan. Before any action, an agent must gather and synthesize relevant information, known as context assembly. This involves collecting data from various sources, internal memory, external databases, specialized APIs, and real-time sensor feeds. The assembled context critically informs planning and decision-making, ensuring the agent operates with a comprehensive understanding of its environment. Incomplete or inaccurate context can lead to flawed reasoning and detrimental actions. Available tools represent the discrete, callable functions or external services an agent can leverage to achieve its goal. These might include data query tools, complex API wrappers, secure code execution environments, or communication interfaces. Each tool must possess a clear interface, rigorously defined inputs, and predictable outputs. The effective selection and utilization of these tools are fundamental to an agent's operational capability, enabling interaction with its environment and data manipulation. Planning is the crucial cognitive process where the agent, based on its goal and assembled context, devises an optimal sequence of actions using its available tools. This often involves decomposing complex goals into manageable subgoals, generating a step-by-step strategy. Advanced planning modules incorporate predictive models and uncertainty estimation to select robust paths. A well-designed planning component mitigates impulsive actions, aligning agent behavior with long-term objectives, crucial for multi-step tasks. Tool orchestration precisely executes the determined plan by sequentially invoking selected tools, handling their inputs and processing outputs. This component meticulously manages execution flow, ensuring all prerequisites for each tool call are met and results are correctly routed for subsequent steps or verification. Effective orchestration minimizes execution errors, ensuring the agent's actions are coherent and contribute directly to the overall goal. It acts as the loop's operational engine. Verification is the critical process of rigorously evaluating whether agent action outcomes, or progress towards the goal, meet predefined criteria. This can involve simple assertion checks, complex data validation, or even invoking another specialized agent for auditing. Without stringent verification, an agent might proceed with incorrect assumptions or flawed results, leading to system degradation or mission failure. It serves as the primary feedback mechanism and quality gate within the loop's continuous operation. Memory stores the agent's past experiences, accumulated context, and learned strategies for future reference. This encompasses short-term operational memory for immediate loop execution and long-term persistent memory for knowledge retention across multiple loops. Effective memory management enables agents to learn from successes and failures, avoid redundant computations, and adapt behavior, improving efficiency without constant human reprogramming. It provides essential historical context for future decisions. Failures are inevitable in complex autonomous systems. The retry strategy meticulously defines how an agent responds to transient errors or unsuccessful tool invocations. This includes specifying maximum retry attempts, implementing exponential backoff delays, or identifying alternative tool paths. A well-designed retry mechanism improves the agent's resilience and robustness, allowing recovery from glitches without terminating the loop. However, excessive retries can consume resources and mask deeper systemic issues. For sensitive operations or high-impact decisions, human approval mechanisms seamlessly integrate human oversight into the autonomous loop. This can temporarily pause agent execution, explicitly requiring human consent before proceeding. The escalation path defines the precise procedure for seeking human intervention when an agent encounters unrecoverable errors, reaches uncertainty thresholds, or requires decisions beyond its mandate. These components are vital for maintaining control, accountability, and safety in autonomous systems. Stopping rules define explicit conditions under which an agent terminates its current loop execution, having achieved its goal or reached a predefined failure state. Named terminal states formalize these outcomes, clearly distinguishing between success, partial success, failure modes, and conditions requiring human review. Explicitly defining these states prevents indefinite execution loops, enables clear post-execution analysis, and facilitates effective system monitoring, ensuring predictable and auditable agent behavior. Budget constraints define maximum computational resources an agent can ethically and economically consume, encompassing processing cycles, API calls, or explicit monetary limits. Exceeding this budget triggers predefined stopping rules or an escalation path. Observability ensures the agent's internal state, decisions, and actions are transparent and continuously monitorable. This includes comprehensive logging, detailed tracing, and precise metrics collection, allowing engineers to understand agent behavior, diagnose issues, and ensure compliance. Without robust observability, agents become opaque black boxes. Scheduling mechanisms dictate when and how frequently an agent's loop is initiated, aligning with system requirements and resource availability. This can range from real-time event-driven activations to periodically triggered batch processing. Persistent state refers to critical data an agent reliably retains across execution cycles, such as long-term memory, learned parameters, or configuration. Managing persistent state correctly is crucial for maintaining continuity, facilitating learning, and consistent behavior over time. A fundamental principle in robust loop engineering is generator-verifier separation. This architectural pattern mandates that the component generating an action or solution is distinct and independent from the component tasked with rigorously verifying its correctness. This crucial separation minimizes inherent bias, significantly increasing verification reliability and trustworthiness. One agent might propose a system change, while another, using different methods, validates its safety. The 5 operational moves describe a typical cyclical lifecycle within a complex agent system. Discovery involves an agent actively identifying a new problem or opportunity within its operational domain. Handoff then refers to transferring responsibility for a task or sub-goal from one agent to another, often a specialized agent. This modularity allows for efficient task decomposition, leveraging specialized expertise across the agent collective, improving overall system efficiency and scalability. Following discovery and handoff, Subsequent moves refine agent operation. Verification systematically checks action results or subgoals against predefined success criteria. Persistence then ensures critical information, like successful outcomes, updated learned parameters, or system state changes, is securely stored and accessible for future use. Finally, scheduling determines when the next relevant agent loop initiates, reactively to new triggers or proactively based on learned patterns. These moves form the backbone of a dynamic, responsive agent ecosystem. Before implementing loop engineering, harness engineering establishes the essential foundational environment. This involves setting up the secure execution sandbox, defining API access, configuring robust monitoring and logging tools, and establishing precise communication protocols between agents and the outside world. Harness engineering creates the controlled, observable, and safe operational substrate upon which autonomous loops reliably function, essentially building secure infrastructure and guardrails for agent deployment. The verification ladder proposes a tiered validation approach, from simple syntactic checks to complex semantic and behavioral tests, increasing rigor as action impact grows. Concurrently, the smallest useful loop advocates for designing agents with minimum viable functionality to achieve a tangible goal. This iterative approach facilitates rapid development, easier debugging, and reduces inherent complexity in launching sophisticated autonomous systems, fostering incremental and controlled deployment. Common loop engineering anti-patterns include infinite loops where stopping conditions are inadequately defined, context bleed where irrelevant information pollutes decision-making, and tool sprawl where an agent has too many undifferentiated tools. Another issue is verification debt, accumulating unverified assumptions. Designing against these anti-patterns, by strictly adhering to a loop specification and employing generator, verifier separation, is crucial for building reliable and manageable autonomous AI agent systems.